Good morning, chemistry students. Here is your last set of notes of Chemistry 1B. I'm sure you're quite excited about that. And we're finishing up our stoichiometry problem, okay? A stoichiometry chapter. So this is wrapping up our stoichiometry chapter. By calculating percent yield. And again, for those of you who are going to continue and take a chemistry class at the college level, and a chemistry class at the college level will likely require a lab, one of the calculations that you do for most every lab at the college level is calculate a percent yield. So, this is, again, information that is going to be useful to you. Again, I would suggest you have out your periodic table with your helper sheet, your polyatomic ions you're supposed to have memorized, your calculator, okay, your chemistry toolkit with your conversion factors on it, because again, all those things will be somewhat helpful as we talk about percent yield. So remember we talked about how to figure out the limiting reagent and the excess reagent. Now we're going to kind of use that information to calculate percent yield. And so we're going to start by talking about our definition of what theoretical yield is. Theoretical yield is defined as, okay, the maximum amount of product that could be formed from the given amounts of reactants. So this is not anything new, okay? This is actually what you have been calculating. So theoretical yield, this is what you calculate when you use a balanced chemical equation. Okay, this is what you've been calculating. So all of the example problems that we've done throughout our notes, we could actually go back and say anytime that we've calculated a product, that you've actually calculated the theoretical yield of that product. Anytime you use your balanced chemical equation to calculate the amount of a product, you have calculated the theoretical yield. So you calculate this every time you use your equation and stoichiometry to calculate the amount of product. So again, all of the problems we've done throughout here, when we've calculated the amount of product, we really have calculated the theoretical yield of that product. So what then is actual yield? Actual yield is defined as the amount of product that actually forms when the reaction is carried out in the lab. Now, because you don't have labs in your home, and if you do, I don't want to know about it, okay? Because you don't have a lab in your home, this is information that has to be given to you, okay? So this information must be provided in the problem. Now, when you're in college and taking a college chemistry class and doing labs, when you do your lab and you measure the amount of product you produce, that would be your actual yield. But for us, we're done doing labs this trimester. So how will this information be given to us? It's going to be given to you in your problem. It's going to tell you what the actual yield for the reaction is. Okay? So it must be given in the problem. Your actual yield is often less than your theoretical yield. And what are some reasons for that? Okay. Well, perhaps the reaction didn't go to completion. Which basically means that the reaction, for some reason, it didn't finish happening. Okay. Sometimes it's because there's some sort of side reaction. So you produce your product, but then your product reacts with something else and becomes something else. Maybe you've had a loss of product. This happens a lot in high school chemistry classes and even in college chemistry classes. Like somehow you accidentally dump something and you don't mean to, and so you've lost your product. Or you washed it out and you thought you had all your product. So there's lots of reasons why this might happen. Most times your actual yield is less than your theoretical yield. Sometimes it's more. And again, why might that be? Well, perhaps you have an impure product. And so you're actually not just measuring the product, but some other products that are produced. And so your mass is more than what it should be, but it's actually not just the product you think it is, it's that product and something else in there. So again, actual yield for you doing problems, that information will be provided in the problem. So we use theoretical yield and actual yield to calculate our percent yield. The definition of percent yield is that it is a ratio of actual yield to theoretical yield expressed as a percentage. Again, part of the reason that people in industry, so again, people employed by chemical companies or pharmaceutical companies, again, percent yield is always something that they're calculating because it measures the efficiency of the reaction. Okay, so it measures how well the reaction occurs. Now, oftentimes, if you have a better than 50% yield, you have a pretty efficient reaction. Okay, but the idea is that this is telling you like how much of your reactants that you start with actually become products at the end, right? A 50% yield means only half of what you start with becomes useful product. The other 50% is lost as waste. So again, this is kind of a big deal when you're working in chemical industry, right? And you're trying to produce products. You don't want to have waste. And so there might be multiple ways to produce something, and you're going to look at doing that in the way that is the most efficient. And so basically, you'd be looking for the way that produces the largest percent yield. This is something that you're going to calculate, so there's an equation for it. The equation is that percent yield equals your actual yield divided by your theoretical yield times 100. So, again, let's take a look at an example of this. For example, we're going to say if 75 grams of iron 2 carbonate is heated with excess oxygen, 45 grams of ferric oxide is produced as well as carbon dioxide. What is the percent yield of this reaction? Again, we're in the chapter about stoichiometry. Remember, the first thing we need to do any of these problems is a balanced chemical equation. So, again, 75 grams of this carbonate is heated, so iron 2 carbonate, that's an ionic compound, so iron is Fe. It has a charge of +2. Carbonate you have memorized is CO3. It has a charge of -2, so it just is going to be FeCO3. Is heated with excess oxygen, so oxygen is another reactant. We produce ferric oxide, so we're probably going to have to use our helper sheet here, right? And ferric, that's a Latin name. So fer is iron. Ic remembers the higher charged iron, so on your helper sheet, the two charges of iron are +2 and +3, so this would be iron with a +3 charge. Oxide is O, charge of -2, so this is going to be Fe2O3, as well as carbon dioxide, so CO2. So now we need to look at balancing this equation. Okay. So 1 iron, 2 irons, so we're going to put a coefficient of 2 in front of iron carbonate, our iron 2 carbonate. We have 1 carbon, we have 1 carbon. So now we have 2 times 3, which is 6, plus 2 more makes 8. Here we have 3 and 2. So the 2 here doesn't really work. So let's go ahead and try a 3. So if I put a 3 here, well, I can't really do 3, right? Because that's not going to work. I need an even number, so I'm not going to use a 3. Let's try a 4. So I have 4 irons. So to get 4 irons on my product side, I need a coefficient of 2 in front of my ferric oxide. So now I have 4 carbons, so I need a coefficient of 4 in front of my carbon dioxide. So now I have 4 times 3, which is 12, plus 2 oxygens. I have 2 times 3, which is 6, and 4 times 2, which is 8. So right now I have 14 oxygens. So the way to fix that is to go ahead and put, oh no, I'm balanced, right? Because I have 12 plus 2, which makes 14. So this is my properly balanced chemical equation. So just cleaned that up a little bit. Now I have 75 grams of this. is heated with excess. Why do we tell you excess? Well, so that you don't have to do a limiting reagent problem first, right? That means this is my limiting reagent and oxygen is my excess reagent. 45 grams of this is produced, as well as carbon dioxide. We want to know the percent yield, and it's really asking for the percent yield of this product. Now, how do I know it's the percent yield of that product? Because it's given me this, and remember, I don't have a lab. So this is my actual yield. So I need to figure out, right, to do my percent yield equation. I know my equation is my actual yield over my theoretical yield times 100. So I've got my actual yield, right? It's 45 grams of ferric oxide. I need my theoretical yield. So remember, that's something we're going to calculate. We're going to calculate it using the limiting reagent. So we're going to take our 75 grams of FeCO3 and calculate how many grams of our ferric oxide, our Fe2O3, we produce. This is our theoretical yield, right? It looks like what we've been doing. So we start with our 75 grams. We're going to use molar mass to convert grams to moles. Our only way to go from one substance to another is with our mole ratio. So we're going to put moles of our iron carbonate to moles of our ferric oxide. And I'm just going to kind of go down here so I have a little bit more room. So moles of ferric oxide are on the top, so that has to go on the bottom. And I know I need to go to grams because the percent yield was given in grams. If it had been given in moles, I'd just be able to do it in moles. So in my molar mass conversion factor, remember the easy number is 1 in front of moles. To get my mass, I'm going to use my periodic table and add up the masses. So for iron, it's 55.845, and I just have one iron. For carbon, it's 12.011, and I just have one carbon. And for oxygen, it's 15.999, but I have 3 of them, so I have to multiply that by 3. And I'm just going to kind of try to write it all because I like to just use those whole big numbers, 115.853 grams. It never hurts to use more decimal places and significant figures. So now in my mole ratio, remember that comes from my coefficients. So in my balanced equation, my coefficient on my ferric oxide was 2, and on my iron carbonate it was 4. So this was a coefficient of 2, this was a coefficient of 4. Again, now I'm back to another molar mass. So again, my moles is easy, that's 1. Okay, my grams, again, I have to calculate. So I have iron, which is 55.845, but I have 2 of them in this compound, plus 15.999 for oxygen, but I have 3 of them. And so I get 159.687 grams. So now I'm ready to put this in my calculator. So remember, I'm going to take 75, multiply it by 2, multiply it by 159.687, and divide that by 115.853 times my 4. So 75 times 2 times 159.687 divided by, I need my parentheses, and I want to have three significant figures. I got 51.688, so I'm going to call that 51.7 grams of Fe2O3. Remember, this is my theoretical yield. So now I have the theoretical yield that I need here. So I'm going to take my 45 and divide it by that answer and then multiply it by 100. Okay? And I want to still have three significant figures, so I got 87.06. So I'm going to call it 87.1%. And I often like to put what substance it is behind it, so it's percentage of my ferric oxide. So the one way that your textbook will make this more challenging is that instead of telling you which one's the limiting and excess reagent, there might first be a problem, part of the problem be that you have to figure out which one's the limiting reagent, like you've done on previous problems. So your homework is on page 259, 29 through 32. Again, you need to show all your work like the work you've just shown me, or I'm just showing you on your outline and throughout your outline. And again, do not type this. Okay, it's too much work to type it, just handwrite it. Take a picture of it or scan it and turn it in. Have a great day. I'll talk to you tomorrow.